Alright, so welcome to this episode of Physics Bonus Content. So if you're here, it's because you are interested in knowing where the centripetal acceleration equation comes from. Again, it's not necessary that you know this, but it is interesting if you're curious about it. So here's the idea. We're going to imagine an object that's going around in a circle like this. So an object that's going in a circle, right, it'll be here at one point, and maybe it'll be here a moment later. And which way is that object going? Well, at this point, it's got a velocity vector. It's kind of going this way, and now it's going this way. So my velocity changes directions as I go around the circle. And I'm going to look at it at these 2 points in time. I'm going to say this is the first time I'm looking at, so I'm going to call it v0, and I'm going to say this is my final velocity, v. And then the other thing I'm going to do here is I'm going to say that there's two radii that I can draw here. So they're both the radius, so they should be congruent. And then this angle that I travel through, I'm going to call this angle theta that I travel through, right? Now, if you remember, vectors have magnitude and direction. They don't have position. So I could take these two vectors and I could redraw them like this. I could take one like this and I can make it point the same direction, but put it over here. And I'm going to take this one and I'm going to put it the same direction and I'm going to put it over here. Now, one thing that's interesting is that if I have uniform circular motion, the magnitude of both these vectors are the same. The only thing that's different is their direction. So the magnitude of these are the same. Now I'm going to define one more vector here. And I'm going to define this vector, and I'm going to call it the delta v vector. And the reason I'm going to do that is because then I can write a vector equation that makes sense. I should be able to say v0 plus delta v. Now, v0 plus delta v equals v, right? Because these are the two that are tip to tail. v0 and v are tip to tail, and they add up to v. So this is the vector equation that then I can write. Okay. Now, what we can show here is that we can show that this triangle here that's made between these two radiuses and this secant line, right, is going to be similar to this triangle. Here's why. If you remember from geometry, tangent lines are always perpendicular to radii. So these two this is a right angle, this is a right angle. And if that's the case, if this line slides over to this line, then this vector would slide over to that vector. So we can say that this angle is also theta. Now look what we have here. We have two isosceles triangles, because radius are the same length and an angle. And we have this isosceles triangle, because remember we said these two velocities are the same magnitude, and we have the same angle. Whenever you have that, you've got similar triangles. So one thing that's nice about similar triangles is that their sides are proportional. So the next thing I can say here is that, okay, let's look at this. I'm going to look at this side and this side. So I'm going to call this side R. And I'm going to call this side, this is, let's just call it little L, because it's approximately the length that I travel. Okay? So I can say R over L is equal to the same two on this triangle. So it's going to be equal to, let's say, V over delta V. Right? And maybe to illustrate my point, let's look at these two. Let me just re-say what I was saying. Instead of doing the two that I highlighted, let's do this one and this one. So we've got R over L is going to be equal to V over delta V. Okay, that's true because those are similar triangles. All right, so now what? Now I can say, but think way back to chapter 2, we learned an equation that the acceleration is defined as delta V over delta T, right? what is delta V here? So if I just do some rearranging of this equation, I should get that delta V is equal to what? VL over R, I think. Right? So I can plug that in now here, and I can say that A is equal to VL over R divided by delta T. Okay? Next thing, what is this? L over delta T? That's basically a distance divided by time, so that's basically a V. So now I have V over R times V, which simplifies to V squared over R, which is my centripetal acceleration equation. And remember, I say QED, which is Latin for quod erat demonstratum. It means that which was to be demonstrated. I demonstrated that which I tried to demonstrate. I proved that the centripetal acceleration is equal to V squared over R.